In 1974, humanity pointed a radio telescope toward the great star cluster M13 and for the first time sent a deliberate greeting into the void. It was not a plea nor a declaration, but more of a ceremony, a symbolic gesture to prove we could. The target itself was unreachable. M13 lies some 25,000 light-years away, so far that even if our message arrived intact, no answer could ever return within the lifetime of our species. But what we didn't consider were the closer neighbors, those who might have been eavesdropping long before we ever composed that ceremonial broadcast. Because the truth is, for more than a century, we've been shouting into the cosmos without meaning to. Every baseball game carried by radio waves, every sitcom bouncing off the stratosphere, every planetary radar pulse aimed at a wandering asteroid, all of it has been leaking into space, spreading outward in a growing sphere of human chatter. For 123 years, we have been speaking to the universe without its consent, and without truly knowing who or what might be listening. Then came 2017. Strange interstellar objects began entering our solar system. First, Oumuamua, then Borisov, then Atlas, each one more enigmatic than the last. Were they natural wanderers, or messengers responding to our long, accidental confession of existence? What if these weren't coincidences at all, but the universe's way of whispering back, "Message received"? Stay until the end to discover how our century of cosmic conversation may already be echoing with replies. Now prepare yourselves. We begin. Part 1. Shouting into the Dark. In 1972 and 1973, humanity launched Pioneer 10 and 11, two spacecraft each carrying a golden plaque bolted to their frames. Etched into those plates was a story about us. A message meant for no one in particular, yet written as if someone might one day find it. The plaques depicted the figures of a naked man and woman standing upright beside a simple outline of the spacecraft for scale. The man's hand was raised, not in surrender, but in what we hoped would be interpreted as a gesture of greeting. Optimistic, perhaps naive, but undeniably human. Alongside them, engravings showed the spin-flip transition of hydrogen atoms, a universal clock and ruler in one, providing any future finder with a shared reference for time and distance. The plaques mapped our solar system, highlighted Earth as the third planet from a modest star, and quietly whispered into the void, "This is where we are, and this is who we are." The effort was bold, but it was only the beginning. Just a few years. Later, in 1977, the Voyager spacecraft set off with something even more ambitious, the Golden Records. Unlike the plaques, these weren't just static diagrams, but time capsules encoded with the richness of life on Earth. The discs carried greetings in 55 languages, the sounds of whales and crickets, laughter and thunder. They spun with 116 images that illustrated our science and our humanity, mathematics and physics, the double helix of DNA, the stages of human reproduction, the warmth of family groups, the geometry of our architecture, and the art and music that revealed our capacity for beauty. Chuck Berry's Johnny B. Goode danced beside Bach, Blind Willie Johnson, and traditional songs from across continents. Carl Sagan, who led the project, called it a message to the universe. Others, more skeptical, dismissed it as cosmic graffiti. But in truth, both descriptions capture something essential about the human urge to reach outward. Yet the most concentrated shout came not from a spacecraft, but from Earth itself. In 1974, Frank Drake and his colleagues at the Arecibo Observatory turned the world's most powerful radio dish toward the globular cluster M13. They transmitted exactly 1,079 bits of information, a number chosen carefully, the product of two prime numbers, 23 and 73. This mathematical clue would signal to any receiver how to arrange the bits into a rectangular grid, which would reveal a pixelated picture of human knowledge. Within that simple grid hid our number system, the blueprint of DNA, a crude human figure, and a sketch of the solar system with Earth carefully marked. For exactly 3 minutes, powered by nearly 1 million watts, the Arecibo dish became the brightest beacon in our galactic neighborhood. The signal raced toward M13 at the speed of light, even though its target lay 25,000 years away, so distant that human civilization will have risen and fallen many times before the message could ever arrive. Still, we sent it, because sometimes the act of calling matters more than the hope of an answer. This impulse wasn't born in a vacuum. 15 years earlier, Giuseppe Cocconi and Philip Morrison had already argued in Nature that radio waves were the natural medium for interstellar communication. They pointed toward a quiet stretch of the spectrum between 1.42 and 1.66 GHz, bracketed by the emission lines of hydrogen and the hydroxyl radical, the building blocks of water and thus of life. They called it the waterhole, reasoning that any civilization with a grasp of chemistry would recognize its significance. The hydrogen line, at precisely 1420.4 MHz, became particularly iconic. It represents the subtle energy shift when a hydrogen atom's electron flips orientation relative to its proton's magnetic field. Hydrogen is the universe's most abundant element. Its transition is its most fundamental whisper. If the cosmos had a shared language, hydrogen would be its alphabet. Decades of SETI research have followed that logic. Radio telescopes tuned to the hydrogen line scan the skies, hoping to catch the faintest artificial whisper. The Breakthrough Listen initiative now monitors millions of stars across multiple frequencies, applying machine learning and vast computing power to sift through cosmic static. The reasoning is elegant. If you want to be heard across interstellar distances, you transmit where the galaxy itself is quiet. But here's what our own experiments have revealed. Our transmissions are surprisingly hard to hear. Television and radio signals, once they escape Earth's atmosphere, fade into the cosmic background within a few light years. The unforgiving math of the inverse square law ensures that with every doubling of distance, the signal strength falls to a quarter. Only our most powerful blasts, the planetary radar pings from Arecibo's S-band transmitter or Goldstone's X-band array, shine bright enough to be detected across interstellar distances. These radar systems, built to map asteroids and chart planets, inadvertently act as lighthouses, sweeping beams of power into the dark. Every time Earth rotates, they carve a signature through space that would be unmistakable to anyone listening nearby. Over time, this infrastructure has grown into the Deep Space Network. 3 colossal antenna complexes, one in California's Mojave Desert, one near Madrid, Spain, and one outside Canberra, Australia. These dishes, some stretching 70 meters across, are designed to maintain constant contact with robotic explorers at the edge of the solar system. But to an alien telescope, they would reveal something else entirely. A planet busy with structured emissions carriers rising and falling, FM radio and television signals neatly slotted into their bands. From afar, Earth would not sound like a natural object at all. It would sound like intention, like technology, like life. Brief, intense radar pulses sweeping across the sky in regular patterns. All of it clustered around a small blue planet, one that seems unusually noisy in the radio bands. The International Telecommunication Union recognizes this strange duality. On the one hand, they protect certain frequencies for radio astronomy, ensuring that at least a few precious windows of silence remain clear for us to hear the universe. On the other, they enforce radio quiet zones around major observatories, oases of electromagnetic stillness. The largest, the National Radio Quiet Zone in West Virginia, spans 13,000 square miles around the Green Bank Observatory, an island of silence in a sea of chatter. Globally, the United Nations Office for Outer Space Affairs coordinates international space policy, its mandate centered on the peaceful use of outer space. But their frameworks assume human actors bound by human laws. They were never designed for incoming messages from other stars. And here lies one of SETI's deepest tensions. Traditional SETI has always been about listening, silent vigilance. Breakthrough. Listen alone processes petabytes of data from radio telescopes across the globe, hunting for patterns that do not belong. The Allen Telescope Array in Northern California, 42 dishes working in unison, sweeps the heavens in search of something unmistakably artificial. But there is another camp, active SETI or METI, messaging extraterrestrial intelligence. Scientists who argue that if all civilizations simply listen, the galaxy may remain locked in silence forever. Someone, they insist, must speak first. Yet their proposals stir unease. High-power transmitters capable of interstellar communication fall under the same regulations as potential weapons. And beyond the technical hurdles lies the philosophical one. Who gave us the right to speak for Earth? Should a handful of scientists and engineers decide when and how to announce our existence? History counsels caution. In 1967, Jocelyn Bell Burnell detected a radio signal so precise it pulsed every 1.337 seconds, like clockwork. The Cambridge team half-jokingly labeled it LGM-1 Little Green Men 1. For a brief moment, they wondered if they were eavesdropping on a galactic civilization. The truth was stranger in its own way. It was the first pulsar, an ultra-dense neutron star spinning faster than the blades of a jet engine, its radio beams sweeping past Earth like a lighthouse in the dark, a reminder that nature, too, can mimic intelligence. Then came 1977 and the famous WOW signal. For 72 seconds, the Big Ear Radio Observatory in Ohio recorded an extraordinarily strong, narrowband signal right near the hydrogen line, the very frequency SETI had predicted alien transmissions would appear. Astronomer Jerry Amon circled the data printout and scribbled a single word in the margin. Wow! The signal was everything SETI researchers had been waiting for, except repeatable. Despite decades of searching, it was never heard again. To this day, it stands as one of astronomy's greatest mysteries and one of its most sobering cautionary tales. These experiences hardened the field. Extraordinary claims demand extraordinary evidence. Every candidate signal must be repeatable, detectable by independent observatories, and proven to be extraterrestrial in origin. The Rio scale now ranks possible detections from 0 to 10, weighing both their credibility and their potential impact on civilization. Most candidate signals rank a mere 1 to 3, interesting but inconclusive. A true alien signal would score an 8 or 9, representing nothing less than a turning point in human history. Meanwhile, culture has been preparing us for decades. From Orson Welles' War of the Worlds in 1938 to films like Contact and Arrival, we have rehearsed first contact scenarios in our imaginations. Pop culture shapes our fears and our hopes, painting alien contact as sudden, dramatic, transformative. Yet real SETI is far subtler, faint whispers across interstellar distances. The archaeological traces of technologies long dead. The silent drift of objects, not quite natural, not quite artificial. But here is the unavoidable truth. Shouting into the dark eventually leads to a single, unnerving question. What if someone is listening? For more than a century, our bubble of radio noise has been expanding at light speed, carrying the sounds of human civilization outward. Baseball games, sitcoms, radar pulses, and deliberate signals, all racing across the void. Each year, our presence washes over new solar systems. If someone was listening, they've already had decades to prepare their reply. The physics are simple. Light speed is fast, but not infinite. If a nearby star had heard us, its answer could already be on its way. The question that keeps SETI scientists awake at night is not whether intelligent life exists elsewhere. Statistically, it almost certainly does. The question is simpler, far more unsettling. What if someone finally picked up? Part 2, the first answer. Night and the birth of 3 Atlas. July 1st, 2025. In the dry mountains of northern Chile, the Atlas telescope scanned the southern sky, doing what it was designed to do, searching for anything that moves too fast or shines too bright. The asteroid Terrestrial Impact Last Alert System operates 4 robotic observatories across the world, their cameras clicking every 30 seconds, capturing vast swaths of the night. Algorithms compared each frame, flagging anything that moved against the stellar backdrop. At 3:42 UTC, Atlas 4 detected something unusual in the constellation Microscopium, a point of light moving too fast, too precisely, faster than any asteroid should move. Already inside the orbit of Jupiter, closing in. By morning, other observatories confirmed it. Pan-STARRS in Hawaii, Zwicky in California. The object was real, it was fast, and its trajectory was wrong. Not an asteroid, not a comet, something from interstellar space. 3 independent observatory systems detected the same anomalous mover, instantly eliminating the possibility of instrumental error or stray cosmic ray hits on the detectors. The Minor Planet Center in Cambridge, Massachusetts, the world's central clearinghouse for asteroid and comet discoveries, ran the orbital calculations. The numbers came back with a troubling result: an eccentricity of 147 and a hyperbolic excess velocity of nearly 15 kilometers per second. This object wasn't bound to our Sun. It was an interstellar visitor following a hyperbolic trajectory that would carry it briefly through our solar system before vanishing back into the galaxy. The discovery triggered an international scramble. Major observatories across the globe reoriented their instruments. The European Southern Observatory's Very Large Telescope in Chile tracked the object, with its 4 8.2-meter mirrors working in perfect concert. The Keck Observatory in Hawaii joined, deploying adaptive optics to sharpen images all the way down to diffraction limits. Even the Hubble Space Telescope received emergency scheduling, a rare privilege to catch this fleeting traveler before it disappeared. The designation arrived quickly: 3I Atlas. The 3I marked it as the 3rd confirmed interstellar object, after 1I Oumuamua in 2017 and 2I Borisov in 2019. Atlas honored the Discovery Survey following tradition, but unlike its predecessors, 3I was bigger, brighter, and its behavior defied conventional physics. Oumuamua had been a tumbling, elongated rock the size of a city block. Its light curve suggested extreme geometry, at least 5 times longer than it was wide. It reflected sunlight in strange ways, unlike any asteroid or comet catalogued before. Most puzzling of all, it showed signs of non-gravitational acceleration. Tiny but measurable pushes that could not be explained by the sun's gravity alone. In 2018, Marco Micheli's team at the European Space Agency published a landmark paper in Nature, documenting systematic deviations from purely gravitational motion. The accelerations were minuscule, about 5 × 10⁶ meters per second squared, 10,000 times weaker than Earth's surface gravity, yet statistically undeniable. Some argued it was cometary outgassing, sublimating ice, pushing it forward like invisible thrusters. But no comet tail was ever observed. Others proposed more radical ideas, perhaps a fragment of an alien light sail, or debris from a shattered body of exotic composition. By contrast, 2I Borisov behaved almost reassuringly. A proper comet from interstellar space, complete with a coma, and tail exactly as textbooks predicted. Its composition, water ice, carbon monoxide, organic molecules, was strikingly similar to comets of our own solar system, natural, familiar, comforting. Atlas, however, fell somewhere between these extremes, and that made it both scientifically fascinating and deeply unsettling. Early photometry revealed a light curve unlike anything in astronomical catalogues. Most asteroids tumble chaotically, their brightness rising and falling as irregular shapes catch the sunlight. But 3I's light curve was different, quasi-periodic, almost mechanical. The brightness varied with a primary cycle of about 7.3 hours, but layered within were subtle oscillations, suggesting complex geometry or even engineered surfaces. Stranger still, the rotational periods remained astonishingly stable across weeks of observation. Natural tumblers drift over time. This one held steady, as if something was managing its orientation. Spectroscopy deepened the mystery. ESO's instruments revealed only faint traces of gas emission, even as the object swung close to the sun. Most comets bloom with spectral fingerprints, lines of water vapor, carbon monoxide, cyanide, and dust. 3I Atlas remained spectrally quiet. Its reflected light didn't match any known asteroid or comet type. Too red for ordinary silicate rock, too strange for organics. Absorption features hinted at exotic carbon compounds, or something processed, something artificial. Radio astronomers soon joined the chase. Goldstone's 70-meter deep space network antenna painted the object with radar at 8.56 GHz, the same frequency used to map Venus and near-Earth asteroids. The echoes that returned were unnerving, not the diffuse scatter expected from a rough rock, but sharp, mirror-like reflections, surfaces that appeared unnaturally smooth, angled as though deliberately placed. Then came the James Webb Space Telescope. JWST's infrared vision uncovered thermal properties that defied simple physics. On average, 3I Atlas was dark, absorbing most of the sunlight that struck it. But embedded within its thermal glow were bright, needle-like spikes, beams of reflected, infrared radiation that flared and vanished as the object rotated. The signature resembled thin films or engineered coatings able to reflect specific wavelengths while absorbing others. Such optical selectivity is rare in nature. But common in design, ground-based observatories in Chile coordinated relentlessly. Knowing the window to study this object would close by late 2025, even ALMA, the Atacama Large Millimeter Array, joined the campaign, searching for faint molecular lines that might betray its internal composition. Public communication was careful. Space agencies remembered the storm of speculation that surrounded Oumuamua. Press releases emphasized the interstellar origin, the unusual properties, but avoided any hint of artificiality. Yet in private, internal memos were blunt. The object's features were not just unusual, they were unsettling. And then came the radio detections. On July 15th, barely 2 weeks after discovery, multiple radio telescopes scattered across the globe reported the same anomaly, a faint, narrow-band carrier wave, co-moving with 3I Atlas. The frequency was chillingly familiar, 1424 MHz. Just offset from the hydrogen line, the most universal frequency in the cosmos, and the traditional beacon for SETI searches. 3 of the world's great observatories confirmed it simultaneously. The Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, and the colossal Fast Dish in Guizhou, China. Independent detections across continents eliminated every ordinary explanation. It was not local interference, not a stray satellite, not an artifact of faulty electronics. The signal was real, and it was coming from humanity's third interstellar visitor. For radio astronomers, interference is the constant enemy. Cell towers, satellites, even a microwave oven in the wrong place can mimic the whispers of the cosmos. But this signal passed every filter, every test. It appeared only when antennas were pointed directly at 3I Atlas. It Doppler shifted in perfect synchrony with the object's motion. Its intensity and frequency remained astonishingly stable across session after session. At first, the tone was pure, a clean, razor-thin spike of energy drifting predictably with orbital mechanics. No modulation, no data, just presence. But its stability was unnatural. The frequency precision rivaled atomic clocks, an oscillator. To a reference far beyond, what natural plasma interactions could produce. The reaction of the scientific community was cautious, almost reluctant. Extraordinary claims demand extraordinary evidence. Pulsars, masers, magnetospheric plasma all can produce narrowband emissions, yet never here. Never at the hydrogen line. It was the choice of frequency itself that unsettled. Why broadcast so close to the most recognizable marker in the spectrum unless you wanted to be found? Confirmation poured in from observatories worldwide. One by one, the possibility of error collapsed. 3I Atlas wasn't just reflecting sunlight, it was transmitting. Governments tried to contain the discovery, classifying internal reports within hours. But in the age of global networks, silence is fragile. News leaked. Social media erupted before official channels could react. Hashtags trended. The reply? They answered. YouTube filled with shaky amateur analyses claiming proof of contact. Within days, the object had a dozen unofficial names. The messenger, the visitor, the reply, amateur radio operators joined the chase. Using cheap software-defined radios, thousands tuned their antennas to 1420 MHz, eager to capture even a whisper of the cosmic tone. For the first time, participation in a possible extraterrestrial contact wasn't limited to world-class observatories. It was democratized, global. Anyone with a receiver could listen. Official statements remained careful. NASA and ESA releases spoke of preliminary detections, of the need for caution, of further verification required. But behind closed doors, tone shifted. Internal memos spoke bluntly of the unprecedented, an interstellar object transmitting intentionally on the frequency we had always imagined as a cosmic calling card. And inside the Planetary Defense Coordination Office, the questions turned darker. For years, their mission had been simple: catalogue and track natural threats, asteroids, comets, impactors. But now they faced a new category. How do you assess the threat level of something that might be under intelligent control? Radio signals, television broadcasts, deliberate messages like the Arecibo transmission. Now perhaps someone had finally called back. The premise of what followed was both simple and profound. For the first time in human history, we would explore the possibility that an interstellar visitor was not just a cosmic accident, but an answer, our response to our own transmissions into space. Every observation, every measurement, every analysis would be conducted with rigorous scientific standards but guided by a single question. What if 3I Atlas Hardu's calling and decided to call back? The implications, if true, would reshape every assumption about our place in the universe. We weren't alone. Someone was listening. And they had traveled across a galaxy to let us know they had heard our voice among the stars. But first, we to determine whether we were dealing with an extraordinary natural phenomenon or something else entirely. Something that had crossed the interstellar void specifically to find us carrying a message we were only beginning to understand. Part 3. A wave of visitors, not a one-off. 3 Atlas was not alone. 3 weeks after the initial discovery, automated sky surveys began flagging additional fast-moving objects on hyperbolic trajectories. The detection pattern suggested something unprecedented in the history of astronomy. Multiple interstellar visitors, arriving within months of each other. Their appearance coordinated in ways that challenged every assumption about random cosmic events. 4. I appeared in data from the Catalina Sky Survey on the 22nd of July, 2025. The linear near-Earth asteroid research program detected 5I 2 days later. By August, amateur astronomers with backyard telescopes were contributing to a growing catalogue of interstellar visitors. Their discoveries verified by professional observatories operating telescopes that had cost hundreds of millions of dollars. These weren't random cosmic debris scattered by some distant stellar catastrophe. The objects shared characteristics that became more disturbing with each new detection. First, their approach vectors. Statistical analysis of interstellar object trajectories should show random distribution objects arriving from all directions as they drift through the galaxy's gravitational field. But this group showed loose coordination that violated expectations by orders of magnitude. Their trajectories converged from a cone of sky roughly 15 deg wide, centered on the constellation Lyra, as if they had been launched from the same general region of space. Dr. Alan Fitzsimmons at Queen's University Belfast led the statistical analysis. His team calculated that the probability of such coordination occurring by chance was approximately 1 in 50 million, well below the threshold for claiming statistical significance in any other field of astronomy. Something had aimed these objects at our solar system with precision that spoke to intelligence and advanced technology. More troubling, their perihelia closest approach points to the Sun, clustered within a narrow range of distances between 0, 8 and 1-2 astronomical units. They were threading the needle of Earth's orbital zone, passing through the region where our planet travels around the Sunday. The targeting precision was extraordinary, suggesting knowledge of our solar system's structure and possibly Earth-specific location. The probability of natural interstellar objects accidentally converging on Earth's orbital zone was vanishingly small. These visitors had been directed toward us, their trajectories calculated to maximize observation opportunities from Earth-based telescopes while maintaining safe distances from our planet. Light curve analysis revealed additional patterns that challenged natural explanations, where 3I Atlas appeared to be a thin, rotating panel with controlled attitude. The subsequent objects showed even more exotic geometries. 4I's brightness. Variations suggested a needle-like shape with an aspect ratio approaching 20:1 longer and thinner than any known natural object in the solar system. The photo trick data indicated that 4I was tumbling end over end with a period of approximately 2 hours. But the tumbling wasn't chaotic like a natural collision fragment. The rotation showed characteristics of controlled motion. ASIF internal mechanisms were managing the object's orientation for optimal solar energy collection or communication geometry. 5. I looked like a tumbling shard, its light curve showing complex variations that suggested a partially fragmented structure. Spectroscopic analysis revealed unusual surface properties, materials that might be porous or partially hollow, creating optical characteristics unlike any known asteroid or comet composition. A smaller object designated 6I produced light curves consistent with what astronomers could only describe as a flake, something thin and flexible, rippling as it rotated through space. The brightness variation suggested a sheet-like structure that might be deforming under thermal stress, or actively changing its configuration. These shapes defied conventional asteroid physics. Natural collision fragments follow predictable patterns based on material strength and impact dynamics. Rocky bodies tend to break into roughly spherical chunks. Icy comets fragment along structural weaknesses, but thin film structures, sails, sheets, panels would behave exactly as the observations suggested. The implications were unsettling. Natural processes don't typically produce objects with extreme aspect ratios and controlled rotation states, but artificial constructs designed for interstellar travel might show precisely these characteristics, especially if they were optimized for minimal mass and maximum surface area. Radio telescopes worldwide coordinated their observations, tracking each object as it approached perihelion. The results painted a picture that challenged every assumption about interstellar visitors. Each object produced narrow-band radio emissions near the hydrogen line, but the signals weren't identical. They showed different modulation patterns, different frequency offsets, and different temporal characteristics. The radio signatures suggested a distributed communication system rather than coincidental emissions. 3 Atlas maintained its steady carrier tone at 1,424 MHz. 4 I broadcast at 1,206 MHz with subtle amplitude modulation. 5 I transmitted brief bursts at multiple frequencies across the waterhole spectrum. 6 I produced complex signals that seemed to carry encoded information in both frequency and timing variations. The diversity of signals ruled out simple explanations based on natural phenomena. Plasma interactions or mersions would show similar characteristics across objects with similar compositions and trajectories. But these visitors were broadcasting like members of a coordinated fleet, each one contributing to a larger communication effort. Dr. Elena Vasquez at the Arecibo Observatory proposed what became known as the staging hypothesis. The objects weren't arriving randomly or even as debris from a single catastrophic event. They represented a carefully orchestrated sequence designed to maximize observability and redundancy while minimizing the risk that their message would be missed or dismissed. The staging approach made sense from an engineering perspective. If you wanted to communicate with a newly detected technological civilization, sending multiple messengers would ensure success, even if some were overlooked or misinterpreted. The varied characteristics of each object provided different types of evidence for artificial origins, making it increasingly difficult to dismiss the entire ensemble as natural phenomena. The temporal correlations were equally suggestive. When astronomers reconstructed the launch windows required for each object to arrive at its observed time, assuming interstellar travel velocities of 10 to 20% the speed of light, they found connections to Earth's broadcast history that seemed too precise to be coincidental, i.e., Atlas, if launched from a star system roughly 50 light-years away, would have departed around 1075, the peak era of powerful television transmitters and the first major planetary radar campaigns. 4. Ice timeline aligned with the early space age and the construction of large military radar installations. 5. I corresponded to the period when commercial satellite communications began filling Earth's spectrum with structured signals. It was as if someone had been listening to our growing radio signature and responding in sequence. Each probe launched in response to successive chapters in humanity's electromagnetic story. The visitors weren't just acknowledging that they had heard us, they were demonstrating detailed knowledge of our technological development over several decades. The Atacama Large Millimeter Array in Chile initiated a coordinated campaign to track the objects with meter-scale precision. VLBI, Very Long Baseline Interferometry, combined data from radio telescopes worldwide, creating a virtual dish the size of Earth. The positional accuracy was extraordinary, allowing astronomers to detect tiny course corrections and attitude adjustments that wouldn't be visible to individual observatories. The VBI results confirmed that several objects were making subtle trajectory modifications, small changes in velocity and direction that couldn't be explained by gravitational perturbations or radiation pressure alone. The course corrections appeared purposeful, adjusting the object's paths to optimize viewing geometry from Earth or maintain communication link quality. High-energy astronomy facilities joined the comprehensive monitoring effort. IceCube in Antarctica, designed to detect neutrinos from cosmic events, monitored for exotic particle emissions that might accompany advanced propulsion systems. Air shower arrays searched for correlations between the object's positions and high-energy cosmic ray detections. The results from high-energy observations were contested and controversial. Some researchers claim to detect faint but statistically significant correlations between the visitor's positions and neutrino or cosmic ray events. Others found no such correlations and attributed the claims to statistical fluctuations or systematic biases in the analysis. The debate reflected deeper uncertainties about what technologies the visitors might be using. Conventional chemical or nuclear propulsion would leave no detectable signature at interstellar distances. But more exotic possibilities, antimatter engines, fusion ramjets, or entirely unknown physics might produce high-energy particles that Earth-based detectors could observe. Citizen science mobilized with unprecedented speed and scale. The Zooniverse platform launched interstellar visitors, allowing volunteers worldwide to classify light curves and radio spectrograms. Within weeks, hundreds of thousands of participants were contributing to the analysis, their collective effort representing years of labor that would have been impossible for professional astronomers alone. Community-flagged anomalies often led to priority observations at major observatories. Amateur astronomers discovered subtle variations in signal timing that professional automated systems had missed. High school students identified patterns in radio emissions that suggested encoding schemes more sophisticated than simple carrier tones. The collaborative effort represented the largest coordinated scientific response to a single phenomenon in history. Social media platforms became repositories for observational data and analysis tools. GitHub hosted open-source software for signal processing and orbital calculations. The entire global community was participating in humanity's first systematic study of visitors from another star system. Space operators faced more immediate and practical concerns. The object's trajectories carried them through heavily traveled regions of the inner solar system. Conjunction bulletins went out to satellite operators, warning of close approaches to geostationary orbit and critical spacecraft assets. The visitors posed no direct collision threat, but their unpredictable maneuvering capabilities raised new categories of operational risk. Insurance companies began reassessing their models for space debris collisions and communications interference. What if these visitors weren't entirely predictable? What if they could maneuver more aggressively than currently observed? The possibility of technology beyond human understanding introduced new variables into actuarial calculations that had traditionally focused on natural hazards and human error. The public's reaction swung between wonder and anxiety as more visitors appeared throughout the summer and fall of 2025. Astronomical societies reported record attendance at star parties and observatory open houses. But the same crowds that gathered to glimpse the visitors through telescopes also reflected deeper uncertainties about humanity's place in a universe that suddenly seemed much more crowded. Social media buzzed with theories ranging from rigorous scientific speculation to apocalyptic prophecy. financial markets showed unusual volatility in aerospace and defense stocks as investors tried to gauge the implications of technologies that might be centuries or millennia ahead of human development. Some clearly believed humanity was about to learn something that would change everything. Space tourism companies reported a surge in bookings for suborbital flights, as if getting a little closer to space would provide some advantage when the visitors made their intentions known. Pilgrimage sites formed spontaneously at radio observatories, where visitors could stand near the dishes that were tracking the objects in real time and listen to recordings of their transmissions. The most unsettling aspect was the object's apparent coordination. As more visitors appeared throughout the summer and fall of 2025, their radio emissions began showing temporal correlations that went beyond simple frequency coordination. Brief synchronized transmissions occurred across multiple objects simultaneously, lasting only seconds, but clearly coordinated across millions of kilometers of space. Whatever intelligence had dispatched this flotilla was maintaining active communication between its components. The visitors weren't just broadcasting to Earth, they were talking to each other, coordinating their activities in real time despite the vast distances separating them. The implications for their communication technology and organizational sophistication were staggering. By September, the catalogue included 15 confirmed interstellar objects, with dozens more candidates awaiting confirmation as their orbits became better determined. The sky was filling with artificial visitors, each one broadcasting its presence on frequencies that humans had long considered the natural choice for interstellar communication. The pattern was becoming undeniable. These weren't random cosmic wanderers or natural debris from some distant stellar catastrophe. This was a planned mission executed with precision and coordination that spoke to intelligence and technology far beyond human capabilities. The question was no longer whether someone was trying to communicate with Earth. The question was what they were trying to say, and whether humanity was prepared to listen to a message that might reshape our understanding of intelligence, technology, and our place among the stars. Part 4. A pattern in the noise. Did they hear us specifically? The mathematics were unavoidable, and they told a story that made astronomers deeply uncomfortable. If the visitors had originated from star systems approximately 50 light-years away, they would have needed to detect Earth's radio emissions decades ago to time their arrival for 2025. This raised a fundamental question that cut to the heart of the mystery. When could they have known we were here? Dr. James Chen at MIT's Hack Radio Observatory took on the task of reconstructing humanity's expanding radio bubble decade by decade. The analysis required careful consideration of transmitter power, antenna patterns, and the inverse square law that governs signal propagation through space. Not all of our broadcasts were created equal in terms of their detectability at interstellar distances. Television broadcasts began in earnest in the 1940, but early systems were low power and poorly focused. The signals that leaked into space were weak and would be difficult to detect beyond a few light-years. High-power military radars proliferated during the Cold War, creating stronger signals that could potentially be detected across interstellar distances, but their narrow beams swept across the sky in patterns that might make them difficult to recognize as artificial. By the 1962, our most powerful transmissions, planetary radar systems designed to map Venus and track asteroids, were beaming megawatts of radio energy toward specific regions of the sky. Thesis systems operated at frequencies chosen for optimal planetary observation, but they also created the brightest radio signatures in Earth's history. The Arecibo Observatory, completed in 1963, became humanity's most powerful voice in the cosmos. Its 305M dish could transmit up to 1 million watts of radio energy in a tightly focused beam. When used for planetary radar observations, Arecibo created radio signatures bright enough to be detected by similar facilities across interstellar distances. The timeline was sobering and precise. Any civilization within 50 light years would have detected our early television signals in the 1872nd and 1882nd as those broadcasts completed their journey across interstellar space at the speed of light. Our most powerful radar transmissions would have reached nearby star systems in the 1997 and 2002, providing clear evidence of technological civilization on Earth. But the visitors weren't just arriving at random times. Their approach vectors, when traced backward through galactic space using sophisticated orbital mechanics calculations, pointed towards specific star systems that would have been optimally positioned to observe Earth during our loudest broadcasting periods. The correlation analysis required extreme care to avoid the statistical traps that had plagued other searches for patterns in astronomical data. Dr. Sarah Martinez at the Harvard-Smithsonian Center for Astrophysics led a team that cross-referenced the visitors' origin vectors with Earth's transmission patterns across multiple decades using Monte Carlo simulations to assess the probability of spurious correlations. HD 164595, a sun-like star, 94 light-years away, sat directly in the path of our most powerful Aribo transmissions during the 1972nd and 1982nd. The geometry was perfect when Arecibo pointed toward Venus for radar mapping. Its beams swept across HD 164595's position in the sky. Any receivers in that system would have detected Earth's radar signals with clarity that made their artificial origin unmistakable. Wolf 35 pins only, 9 light-years distant, would have received our television signals with unusual clarity due to its position relative to Earth's rotation axis. Their dwarf star lies nearly perpendicular to our planet's equatorial plane, meaning it would observe Earth from an angle that maximized reception of our strongest commercial broadcast transmissions. Tau Ceti, a favorite target of SETI searches, due to its proximity and sun-like characteristics, aligned perfectly with several major radar campaigns conducted during the 1992 and early 2002. The star system would have received clear evidence of technological activity on Earth precisely during the period when our deepest space missions were beginning to reveal the solar system's structure and composition. The statistical analysis revealed correlations significant at the 4 sigma level, odds of roughly 1 in 15,000 that the patterns were purely coincidental. In particle physics, such correlations would constitute strong evidence for new phenomena. In astronomy, they demanded serious consideration even from skeptical researchers. But critics argued that such analysis was prone to what statisticians call the look elsewhere effect, the tendency to find patterns when you search through enough data with sufficient flexibility in your analysis methods. With hundreds of nearby star systems and decades of transmission history, some correlations were inevitable, even if no real relationship existed. Dr. Robert Hayes at the University of Arizona led the skeptical response. His team conducted parallel analyses using randomized datasets and slightly different statistical methods. They found that apparent correlations could emerge from chance. Alignments combined with observational biases and human pattern recognition psychology. We're seeing patterns because we want to see them, Hayes argued in a widely cited paper published in the Astrophysical journal. Give humans enough data about their own transmissions and some cosmic visitors, and they'll find connections between anything. The universe is under no obligation to care about our radio broadcasts. But the temporal patterns embedded in the visitor's arrival sequence provided more compelling evidence that went beyond simple geometric alignments. The objects didn't arrive at random intervals determined by orbital mechanics alone. Their spacing echoed key milestones in humanity's broadcast history with precision that was difficult to dismiss as coincidence. Dr. Lisa Johansson at the SETI Institute proposed the echo hypothesis, a model that treated each visitor as our response to specific human transmissions. If the visitors were indeed answers to or broadcasts, their arrival timing should mirror our own transmission milestones, delayed by the light travel time between star systems, plus the time required for interstellar travel. She constructed a mathematical model that assumed interstellar travel velocities of 10 to 20% the speed of light, fast by human standards, but achievable by civilizations with advanced propulsion technology. The model predicted visitor arrival times, based on the intensity and timing of Earth's strongest radio transmissions, weighted by the probability that different star systems could have detected those signals. The agreement between predicted and observed arrival times was remarkable. 3 Atlas matched the timeline for air response to Earth's television broadcasting peak in the 1972nd 4. I aligned with reactions to early military radar installations. 5. I corresponded to the commercial satellite communication era. The patterns suggested not just intelligence, but intelligence that had been monitoring Earth's technological development across multiple decades. The most compelling evidence came from information theory analysis of the visitors' radio emissions. Several objects showed transmission patterns that appeared to reference the 1924 Arecibo message, that famous 3-minute broadcast directed toward the globular cluster M13. The Arecibo message had encoded the numbers 1 through 10 in binary notation, followed by atomic numbers for hydrogen, carbon, nitrogen, oxygen, and phosphorus, the key elements. In DNA, it included a representation of the double helix structure, a crude pictogram of a human figure, and a diagram of the solar system with Earth marked as the 3rd planet from the Sunday. Some of the visitors' signals contained similar numerical progressions, but with subtle variations that suggested intentional modification rather than simple repetition or random noise. The binary sequences were recognizable, but extended beyond the original Arecibo format, including mathematical concepts that humans had discovered but not yet broadcast into space. The prime number sequences were particularly striking and represented perhaps the strongest evidence for intentional communication. The Arecibo message had used prime numbers as a universal mathematical concept, something any technological civilization would recognize regardless of their specific counting system or mathematical notation. Several visitors broadcast their own prime sequences: 2, 3, 5, 7, 11, 13, 17, 19, 23, but then deviated from the standard progression in ways that seemed deliberate rather than accidental. It was as if someone was saying, "We received your message and understood your mathematical language. Now let us show you variations and extensions that demonstrate our own mathematical sophistication." The deviations weren't random. They followed patterns that corresponded to advanced number theory. Twin primes, Sophie-Germain primes, mean primes. The visitors were demonstrating mathematical knowledge that went beyond basic counting, showing familiarity with concepts that human mathematicians had developed over centuries of research. Statistical analysis of the mathematical content required extreme care to avoid the seductive trap of pattern seeking in noisy data. Dr. Chen's team pre-registered their hypothesis before analyzing the visitors' transmissions, committing to specific statistical tests and significance thresholds. They used Monte Carlo simulations to assess the probability of finding apparent mathematical patterns in random data. Even with these rigorous safeguards, the connections remained statistically robust. The probability that random radio emissions would contain recognizable mathematical sequences related to human broadcasts was less than 1 in 10,000. The visitors were demonstrating knowledge of human mathematics and extending it in ways that proved their intelligence and technological sophistication, but the skeptical community pushed back hard against these interpretations. The debate played out in academic journals and social media with equal intensity, reflecting fundamental disagreements about how to evaluate extraordinary claims with limited data. Hayes and his colleagues argued that the apparent mathematical content reflected human psychology more than alien communication. Pattern recognition is fundamental to human cognition. They wrote, "We evolved to find meaningful signals in noisy environments. When we look at cosmic phenomena through that evolutionary lens, we're prone to see intelligence even in random processes." The statistical arguments became increasingly sophisticated as both sides refined their methods and assumptions. Supporters of the intelligence hypothesis pointed to the multiple independent lines of evidence, geometric correlations, temporal patterns, mathematical content, and coordinated behaviors across multiple objects. Critics emphasized the dangers of multiple hypothesis testing and the human tendency to find significance in large datasets. The debate attracted attention from philosophers of science and experts in statistical methodology. The National Academy of Sciences convened a special panel to evaluate the evidence and provide guidance for continued research. The panel's preliminary report was carefully worded, but acknowledged that the visitors represented phenomena that merit serious scientific investigation using the most rigorous methods available. Social media amplified the controversy with hashtags like number pattern or pareidolia trending worldwide. Late-night talk show hosts made jokes about humans being synergistic. They assumed every cosmic coincidence was about them. But the scientific community took the analysis seriously, recognizing that even a small probability of intentional contact carried enormous implications for humanity's future. The provisional consensus emerging from months of analysis and heated debate was carefully worded. The correlations between Earth's transmission history and the visitors' characteristics were statistically significant and not easily explained by random processes or observational biases. Whether this represented intentional communication remained an open question, but the patterns were strong enough to justify systematic attempts at response. The phrase "systematic attempts at response" carried profound weight. It implied that humanity might attempt to communicate back to test whether the visitors would react to our transmissions in real time. The idea was both thrilling and terrifying. Our first intentional conversation with intelligence from another star system. After decades of passive listening, we were contemplating active participation in what might be the galaxy's oldest and most important conversation. The visitors had given us what appeared to be their opening statement, demonstrating knowledge of our mathematics, our history, and our location in space. The question was whether we were ready to reply and what we might learn from beings who had mastered the art of communication across interstellar distances. Part 5. Anatomy of an Enigma. What 3 Atlas is physically. By October 2025, the combined observations from dozens of observatories worldwide had compiled the most detailed profile of an interstellar object in history. What emerged was a picture that defied easy categorization. 3 Atlas measured approximately 200 Oumuamua in its longest dimension, with a width of roughly 20 meters and a thickness that radar observations suggested was less than 2 mm. The aspect ratio exceeded 10:1, making it one of the most elongated objects ever observed in the solar system. Its shape was consistent with a thin panel or stack of panels, possibly articulated, able to change configuration. The object's non-gravitational accelerations were subtle but unmistakable. As it approached perihelion, tiny deviations from a purely gravitational trajectory accumulated into measurable course corrections. The accelerations were coherent, always sunward or anti-sunward, never random. They matched the predictions for radiation pressure acting on a highly reflective surface, but the object's measured albedo was too low to account for such effects. Spectroscopic analysis revealed surface chemistry unlike anything in the asteroid catalogues. The spectrum showed absorption features consistent with exotic carbon allotropes, materials that might be engineered rather than naturally occurring. There were hints of boron nitride coatings and traces of metals arranged in patterns that suggested deliberate doping for specific electromagnetic properties. The thermal behavior was perhaps the most puzzling aspect. As 3I Atlas moved through different heliocentric distances, its temperature didn't follow the simple inverse square law that governs most solar system objects. Instead, it showed thermal plateaus, regions where their temperature remained nearly constant despite changing solar irradiation. This suggested active thermal management, possibly through micro-louvers or metamaterial surfaces that could adjust their emissivity in real time. The object's rotation was equally controlled, unlike natural asteroids which tumble chaotically due to collision history and tidal forces. 3 Atlas maintained a stable spin axis aligned with specific celestial coordinates. More intriguingly, its rotation period showed subtle variations that correlated with solar illumination angles, as if the object was adjusting its attitude to optimize solar energy collection or thermal management. The radio emissions remained the most compelling evidence of artificial origin. The primary carrier at 1424 MHz was accompanied by harmonics at precise mathematical intervals. Initially, the signal showed no modulation, just a clean, narrow band tone that Doppler shifted with the object's motion. But as 3 approached perihelion in November, modulation appeared. The pattern was unmistakable. Prime numbers, groups of pulses corresponding to 2, 3, 5, 7, 11, 13, 17, 19. The sequence continued through the first several dozen primes, then repeated. It was the kind of signal that SETI researchers had long predicted as the first communication from an alien intelligence, mathematically sophisticated, but simple enough to be recognized as artificial. Dr. Abraham Lowe at Harvard had proposed several criteria for identifying artificial interstellar objects, including unusual, brightness at large distances, evidence of artificial acceleration, and electromagnetic emissions. 3 Atlas appeared to satisfy all of them. Lowe estimated that if the object's reflectivity was ordinary, its apparent brightness at discovery distance would require it to generate approximately 10 GW of internal power, enough to supply a small city. The mainstream astronomical community remained cautious. Hubble Space Telescope images showed a diffuse coma around 3 Atlas consistent with gas and dust sublimation as the object heated up near the Sunday. The astronomical picture of the day featured these images with captions emphasizing normal cometary behavior. Ground-based observations detected water vapor and carbon monoxide in the object's immediate vicinity, supporting natural explanations. But even normal cometary physics couldn't fully account for all observations. The outgassing was too weak to explain the non-gravitational accelerations. The coma's structure showed asymmetries that suggested controlled venting rather than simple sublimation. Most puzzling, the radio emissions continued even when the object was at its furthest point from the Sun, where natural plasma processes should have ceased. The debate crystallized around competing hypotheses. Natural explanations invoked exotic but plausible scenarios. A fragment from a disrupted comet with unusual composition and geometry, perhaps laced with metallic inclusions that could produce radio emissions through plasma interactions. The controlled rotation and thermal behavior might result from internal structure, cavities, and chambers that created thermal inertia and gyroscopic stability. Artificial explanations were more speculative, but eerily consistent with the observations. An autonomous probe or messenger system, possibly using solar energy for power and attitude control. The thin geometry suggested a deployable structure, perhaps a communication array, designed to maximize surface area for both solar collection and radio transmission. The prime number sequence indicated not just intelligence, but intelligence that understood human mathematical concepts. A third category emerged, something between natural and artificial. Dr. Elena Rodriguez at the University of Barcelona proposed that 3 Atlas might represent technobiotic debris, remnants of abiological civilization that had learned to engineer materials at the molecular level. The object might be partially alive, using biological processes to maintain its structure and behavior across interstellar distances. Risk assessment became a priority as 3IE Atlas approached its closest point to Earth in late November. The object would pass within 3 astronomical units, about 45 million kilometers, close enough for detailed observation, but far enough to avoid any gravitational perturbation of Earth's orbit. More concerning was the possibility of debris shedding. If the object was indeed artificial, and potentially damaged by its long interstellar journey, fragments might separate during perihelion passage. The Planetary Defense Coordination Office issued cautious advisories to space agencies worldwide. While 3I Atlas posed no direct collision threat, its behavior remained unpredictable. The controlled accelerations proved the object could maneuver. The question was whether such maneuvers were automatic responses to solar heating or represented active guidance by some form of intelligence. Companion objects added another layer of complexity. Several smaller pieces designated 3 Atlas A through 3 I Atlas F traveled in formation with the primary object. These sea fragments showed similar radio emissions and coordinated maneuvers, suggesting they might be calibration mirrors or relay nodes for a distributed communication system. Energy considerations painted a sobering picture. The radio transmissions alone required kilowatts of power, substantial for an object with limited solar collection area. If the emissions were indeed intentional communications rather than waste energy, they represented a significant commitment of resources. Someone or something was spending considerable energy to ensure we could hear them as 3 Atlas reached perihelion on the 28th of November 2025. The astronomical community held its collective breath. This was the moment of closest approach maximum heating, and if the object was indeed artificial, perhaps maximum activity. Every major observatory on Earth was watching, waiting to see what humanity's most enigmatic visitor would reveal about itself. Part 6, Talking Back, Protocols, Politics, and the first reply. The moment astronomers confirmed that 3I Atlas was transmitting prime numbers, humanity faced a question it had never seriously confronted. How do you respond to a message from space? The International Academy of Astronautics had spent decades developing post-detection protocols for SETI signals. Their guidelines were comprehensive but advisory, a careful framework for verification, analysis, and eventual response that assumed governments would coordinate through existing treaty structures. But no treaty anticipated visitors that could maneuver and actively communicate while passing through the solar system. The UN Committee on the Peaceful Uses of Outer Space convened emergency sessions in Vienna. COPUOS, as it was known, had handled everything from space debris to commercial launches, but never interstellar diplomacy. The Committee on Space Research, COSPAR, weighed in on planetary protection protocols originally designed to prevent contamination of Mars and Europa. Did those same principles apply to artificial visitors from other star systems? The International Telecommunication Union faced more immediate concerns. Radio frequencies were national resources carefully allocated to prevent interference between terrestrial services. But what happened when an alien intelligence started broadcasting on frequencies reserved for radio astronomy? The ITU's role in protecting SETI bands suddenly became critical to preventing interference with humanity's first conversation with the cosmos. Behind closed doors, the debate was less diplomatic. National space agencies understood that whoever responded first might claim some form of precedent in interstellar communications. NASA's Deep Space Network could reach 3I Atlas with existing hardware. The European Space AI's ESTRAC network provided similar capabilities. China's evolving deep space communication infrastructure was rapidly approaching par with Western systems. but the most powerful transmitters belong to military organizations and academic research institutions. The Arecibo Observatory in Puerto Rico, despite its recent structural collapse, had been the world's most powerful radio telescope. Its replacement, the proposed next generation Arecibo telescope, remained years away. The mantle had passed to other facilities. The 500-meter aperture spherical telescope fast in China, the upgraded facilities at Goldstone and Canra, and university-operated arrays like the Very Large Array in New Mexico. Dr. Jill Tarter, former director of the SETI Institute, emerged as an unlikely coordinator. Her decades of experience searching for extraterrestrial signals gave her unique authority to speak about protocols and procedures. "We've always known this moment might come," she said in emergency meetings with international colleagues. "The question is whether we respond as one species or as competing nations." The technical challenges were substantial but manageable. Any response to 3i Atlas would need to account for the object's rapid motion and changing distance. Doppler compensation required precise tracking and frequency adjustment in real time. The transmissions would need to be powerful enough to overcome interplanetary distances while remaining narrowband enough to be clearly artificial. The communication protocol merged from SETI traditions and information theory. Begin with mathematics, the universal language. Reciprocate the prime number sequence to demonstrate comprehension. Then introduce more complex concepts, atomic structures, physical constants, perhaps even a simple star map showing our position in the galaxy. Content restrictions became a source of heated debate. Military advisors warned against revealing sensitive information about Earth's infrastructure or defensive capabilities. Scientists argued that any civilization capable of interstellar travel would already understand our technological limitations. The compromise was elegant in its simplicity. Respond with the same type of information we had already broadcast deliberately. The mathematical and physical concepts from the 1974 Arecibo message updated with current knowledge. The modulation scheme had Tobe simple enough for any intelligence to decode, but sophisticated enough to carry meaningful information. The team settled on pulse position modulation with heavy error correction, slow, inefficient, but virtually immune to corruption. Barker codes would provide unmistakable preamylase mathematical sequences that could only be artificial. Time was the critical constraint. 3i Atlas would remain within optimal communication range for only a few weeks. The object's high velocity meant that Earth's rotation would provide brief communication windows as different antenna complexes came into view. Dynamic scheduling software, originally developed for tracking deep space missions, was repurposed to maximize contact time with humanity's first interstellar correspondent. Chain of custody protocols ensured that every transmission would be documented and verified. Cryptographic signatures would prevent later claims that the message had been altered or fabricated. Multiple observatories would maintain independent records, creating a permanent archive of humanity's first intentional communication with another intelligence. The decision to transmit came on the 3rd of December, 2025. 3i Atlas was approaching its optimal viewing geometry from Earth, and radio astronomers had confirmed that the object's prime number sequence was continuing with increasing complexity. The visitor was demonstrating mathematical sophistication that extended far beyond simple counting. Dr. Martinez keyed the transmission from the Arecibo replacement facility, now under international coordination. The message began with the same prime sequence that 3i Atlas had been broadcasting, confirming that we had received and understood. It continued with the first few elements of the periodic table expressed in binary notation. Then came a simple representation of the hydrogen atom, the same concept that defined the frequency of our conversation. The response came 18 minutes later, the light travel time to 3i Atlas and back. the visitor's signal changed. The steady prime number sequence gave way to a more complex pattern. Groups of pulses that corresponded to atomic numbers: hydrogen, helium, lithium, beryllium. But then the sequence diverged from Earth's periodic table, including pulse groups that didn't match any known element. It was as if the visitor was teaching us chemistry we hadn't discovered yet. More remarkable was what happened to the object itself. Ground-based telescopes detected a subtle brightening, a brief, shutter-like flash that lasted exactly as long as Earth's transmission. Photo trick analysis suggested that part of 3 Atlas had physically reconfigured itself, perhaps opening reflective panels or adjusting its orientation to create a visual acknowledgement of the radio exchange. The implications were staggering. This wasn't passive reflection of a natural phenomenon. This was active, real-time communication with an intelligence that could coordinate radio and optical signals across interplanetary distances. News of the successful exchange leaked within hours, despite careful classification. Amateur radio operators worldwide had been monitoring the frequencies, and the distinctive pulse patterns were impossible to hide. Social media erupted with excitement and speculation. Governments rushed to issue statements emphasizing caution and international cooperation, but the fundamental truth was unavoidable. Humanity had successfully initiated a conversation with visitors from another star system. The second exchange came 2 days later. This time 3 Atlas initiated the contact, transmitting a more complex mathematical sequence. The pattern appeared to describe orbital mechanics, the motion of objects around gravitational sources. When Earth's mathematicians decoded the full sequence, they realized the visitor was describing not just general orbital theory, but the specific trajectory it was following through our solar system. It was showing us that it understood where it was and where it was going. More importantly, it was demonstrating that its presence in our solar system was not accidental. The trajectory had been calculated, planned, executed across interstellar distances with precision that spoke to technologies humanity could barely imagine. The visitor wasn't just answering our call, it was explaining how it had heard us, traveled, to find us, and positioned itself for optimal communication. The conversation that followed would reshape every assumption about our place in the universe and our future among the stars. But first, we had to understand what 3I Atlas was trying to teach us about the galaxy we thought we knew. Part 7. Earth Reacts, Psychology, Faith, Markets. The moment news broke of successful two-way communication with 3 Atlas, humanity's collective psychology shifted in ways that would take sociologists decades to fully analyze. Mental health hotlines reported a 340% increase in calls during the first week after the exchange became public. The conversations followed predictable patterns: existential anxiety about humanity's place in the universe, profound excitement about the possibilities ahead, and a peculiar form of cosmic loneliness. The realization that we had never truly been alone, but had spent centuries believing we were. Dr. Susan Chen at the Stanford Psychology Institute coined the term contact syndrome to describe the cluster of reactions she observed in her practice. Patients reported vivid dreams about space travel, obsessive sky-watching behavior, and a sudden sense that earthly concerns had become trivial. It's as if people are trying to mentally prepare for a future they can't yet imagine. She noted in her preliminary research, religious responses varied dramatically across denominations and faiths. The Vatican issued a carefully worded statement within 48 hours emphasizing that the discovery of intelligence beyond Earth was consistent with Catholic theology. The universe is vast and full of wonders. Pope Francis declared, if God has chosen to populate it with other forms of consciousness, this only increases our sense of his infinite creativity. Evangelical Protestant reactions were more mixed. Some leaders embraced the visitors as evidence of God's cosmic scope. Others worried about theological implications. Did beings from other worlds possess souls? Had Christ's sacrifice extended beyond Earth? Emergency theological conferences convened in seminaries worldwide, grappling with questions that had been theoretical until now. Islamic scholars found more comfortable ground in the Quran's references to God's creation, spanning multiple worlds. Buddhist leaders spoke of the contact as confirmation that consciousness was a fundamental property of the universe. Hindu traditions, already comfortable with cosmic scales and multiple realms of existence, adapted most easily to the new reality. Financial markets, meanwhile, experienced what economists later dubbed the contact correction. Aerospace and defense stocks surged initially, driven by speculation about new technologies and government contracts, but the gains were volatile, reversing sharply when early analysis suggested the visitors showed no hostile intent. Satellite communication companies saw dramatic shifts in their insurance rates as the possibility of interference, intentional or accidental, from advanced alien technology created new liability categories. Rare earth element prices spiked based on speculation that alien technology might require exotic materials. Lithium used in batteries and electronics doubled in price within a week. Gold, historically a safe haven during uncertainty, showed surprising stability. Apparently, investors believed that beings capable of interstellar travel would be less impressed by shiny metals than previous generations of humans had assumed. The cryptocurrency markets offered a fascinating window into collective psychology. Bitcoin prices soared on theories that decentralized digital currencies might be preferred by interstellar traders. New contact coins appeared daily, most of them elaborate scams, but some reflecting genuine attempts to create communication protocols that might work across species barriers. Information warfare erupted across social media platforms almost immediately. Bot networks, many apparently state-sponsored, flooded Twitter, Facebook, and TikTok with competing narratives. Some claimed the entire contact event was an elaborate hoax perpetrated by world governments to justify increased surveillance. Others insisted the visitors represented an invasion force and demanded immediate military mobilization. Platform moderators found themselves in the unprecedented position of fact-checking claims about alien intelligence. Twitter's policy team worked frantically to develop guidelines for extraterrestrial content while simultaneously trying to combat misinformation about the visitors' intentions and capabilities. Verification badges appeared on official observatory accounts, creating a new category of trusted sources for cosmic news. Educational systems scrambled to respond to sudden student interest in astronomy, radioengineering, and astrobiology. Universities reported unprecedented enrollment in physics and mathematics courses. Community colleges began offering crash courses. In radio technology, teaching students to build their own receivers for monitoring interstellar signals. Children's reactions were particularly telling. Teachers reported that students had begun incorporating space themes into artwork and creative writing with remarkable sophistication. Many children seemed less surprised by the contact than adults, as if they had always assumed the universe contained other intelligences and were merely waiting for grown-ups to figure it out. The art world responded with characteristic intensity. Museums organized emergency exhibitions featuring space-themed works. New compositions appeared almost daily, many incorporating prime number rhythms or the actual radio frequencies detected from 3i Atlas. Visual artists created installations using the hydrogen line frequency as an organizing principle. Saturn found 420 MHz translated into colors, patterns, and sculptural forms. Social rituals emerged organically. Listen parties became popular with groups gathering around radios tuned to frequencies where the visitors might broadcast. astronomy clubs found themselves overwhelmed with new members eager to glimpse the visitors through telescopes. The hashtag number, space, became a global phenomenon, with millions of people posting messages intended for extraterrestrial audiences. Night sky photography exploded in popularity. Amateur astronomers who had never owned a camera suddenly invested in telephoto lenses and tracking mounts, hoping to capture images of the interstellar visitors. The photos themselves were unremarkable, distant points of light indistinguishable from stars. But the act of photography seemed to satisfy a deep human need to document and share this historic moment. Urban light pollution became a political issue for the first time in decades. City councils faced pressure to implement dark sky ordinances, dimming unnecessary lighting to improve astronomical visibility. Hardware stores reported shortages of red flashlights, the preferred illumination for preserving night vision during stargazing sessions. The psychological impact extended to unexpected areas. Marriage proposals reportedly included references to the cosmic perspective. Dating apps added views on extraterrestrial contact to their matching algorithms. Pet adoption rates spiked, possibly reflecting the desire for companionship during uncertain times. Corporate marketing adapted with remarkable speed. Car commercials featured families driving to dark locations for better sky viewing. Smartphone manufacturers emphasized their cameras' low-light capabilities for astrophotography. Coffee companies marketed contact blends for those long nights of sky watching. But perhaps the most significant change was subtler, a shift in temporal perspective. People began thinking in longer timescales, considering decisions in the context of cosmic history rather than quarterly earnings or election cycles. Urban planning discussions included speculation about how cities might need to evolve for a species that knew it wasn't alone in the universe. The psychological research would continue for years, but early patterns were clear. Humanity was not just processing the existence of other intelligence. We were beginning to imagine ourselves as part of a larger community of minds scattered across in the galaxy. The isolation that had defined human consciousness since we first looked up at the stars was finally tentatively coming to an end. Part 8. Building a mission in months, not years. By January 2026, the impossible had become inevitable. Humanity would send a spacecraft to rendezvous with 3I Atlas. The mission architecture emerged from emergency planning sessions that brought together NASA's best engineers, ESA's mission designers, and representatives from commercial space companies that had been quietly revolutionizing access to space. The challenge was unprecedented, intercepting a target moving at interstellar velocities with a launch window measured in weeks rather than years. Traditional mission planning assumed development cycles of a decade or more. The Voyager probes had taken 8 years from concept to launch. The James Webb Space Telescope required 3 decades from initial proposal to operation. But 3 Atlas would not wait for human bureaucracy. By mid-2026, the visitor would be accelerating away from the Sun, beyond the reach of any spacecraft humanity could reasonably construct. The solution lay in leveraging hardware that already existed or could be rapidly modified. SpaceX's Super Heavy booster, originally designed for Mars missions, could deliver substantial payloads to interplanetary trajectories. Solar electric propulsion, systems proven on asteroid missions, could provide the precision navigation required for intercept. The challenge was integrating these components into a functional mission in less than 8 months. Dr. Robert Braun, formerly of NASA's Jet Propulsion Laboratory, led the international mission design team. His philosophy was ruthlessly pragmatic. Using proven technologies, accept higher risks than normal missions, and focus exclusively on objectives that could be achieved during a brief flyby encounter. The baseline mission profile was elegant in its simplicity: a single large spacecraft, would launch in June 2026 following a minimum energy transfer to intercept 3I Atlas in September. The encounter would last roughly 6 hours, during which the spacecraft would deploy multiple small probes designed to approach the visitor from different angles while maintaining safe distances. Guidance, navigation, and control presented the most significant technical challenges. 3 Atlas was a thin, tumbling target with unpredictable maneuvering capabilities. Traditional asteroid flyby missions relied on precise trajectory prediction, but this visitor had already demonstrated its ability to make small course corrections. The spacecraft would need autonomous navigation systems capable of adjusting to target movements in real time. The payload selection reflected urgent scientific priorities. Wideband radio receivers would monitor the full spectrum of emissions from 3 Atlas, searching for communication attempts or information content. Optical cameras with various filters would document the object's physical structure and surface properties. Laser communication systems would attempt to establish high bandwidth contact, testing whether the visitor could respond to optical signals, as well as radio. Most controversially, the mission included microp probes designed for extremely close approach, potentially within meters of 3I Atlas's surface. These contactors were equipped with sampling systems that could collect material if the opportunity arose, but their primary purpose was detailed observation and active signal transmission from close range. The James Webb Space Telescope's role became critical for mission success. JWST's moving target tracking capabilities, though limited to objects moving slower than 75 milliseconds per second, could potentially observe 3I Atlas during specific portions of its trajectory. More importantly, JWST's infrared sensitivity might detect thermal signatures that could reveal internal structure or energy sources. Very long baseline interferometry networks worldwide coordinated to provide micro-arc-second position measurements of 3I Atlas. This precision achieved by combining signals from radio telescopes separated by continental distances would enable trajectory prediction accurate enough for spacecraft intercept calculations. The Rubin Observatory's legacy survey of space and time, scheduled to begin full operations in 2025, offered another advantage. LSST's wide-field surveys might detect future interstellar visitors earlier, providing longer lead times for mission planning. The lessons learned from the 3 Atlas encounter would inform rapid response protocols for subsequent visitors. Sample collection ethics generated heated debate in the scientific community. The Committee on Space Research, COSPAR, had established planetary protection categories for different types of missions, but none addressed the possibility of sampling potentially artificial objects from other star systems. Was 3 Atlas a natural phenomenon that could be studied like any asteroid, or did it represent the property of another intelligence that should be approached with diplomatic rather than scientific protocols? The compromise was cautious. Sampling would be attempted only if 3 Atlas appeared to be shedding material naturally, or if the visitor provided some form of apparent consent through its communication patterns. Direct contact with the primary structure would be avoided unless absolutely necessary for mission success. International coordination proved surprisingly smooth. The scale and timeline of the mission required resources that no single nation could provide quickly enough. NASA contributed launch services and mission operations experience. ESA provided proven propulsion systems and navigation software. Commercial partners supplied communications equipment and computational resources. The arrangement created precedents for future international missions to unconventional targets. Contingency planning consumed enormous effort. What if 3 Atlas changed course unexpectedly? What if it deployed defensive systems or debris fields? What if communication attempts triggered hostile responses? Each scenario required predefined responses. that could be executed autonomously, since the 8-minute communication delay to mission control would make real-time intervention impossible. The encounter timeline was choreographed with military precision. Initial contact would occur at a distance of 10,000 kilometers, well beyond any debris field, but close enough for detailed observation. The main spacecraft would maintain this standoff distance, while deploying microp probes for closer inspection. Active communication attempts would begin immediately, using every available frequency and modulation scheme. As launch approached in June 2026, public attention focused intensely on the mission. Unlike previous interplanetary missions which generated modest public interest, the 3I Atlas rendezvous captured global imagination. The spacecraft carried messages from world leaders, children's artwork selected through international competitions, and symbolic artifacts representing human civilization. The encounter itself would be brief, but unprecedented. For 6 hours, humanity would have its closest look at visitors from another star system. The scientific return might answer fundamental questions about the nature of interstellar objects and the possibility of extraterrestrial intelligence. More importantly, the mission would demonstrate human capability to respond rapidly to cosmic opportunities. But as the spacecraft raced toward its appointment with 3 Atlas, scientists prepared for discoveries that might challenge every assumption about intelligence, technology, and our place among the stars. Part 9, Proof or Pareidolia, the Scientific. Knife edge. The hardest part of extraordinary science is knowing when you found something extraordinary. Dr. Elena Martinez understood this as she stared at the data streaming back from humanity's first interstellar rendezvous. The encounter with 3I Atlas had lasted 6 hours and 17 minutes, producing terabytes of observations that would take months to fully analyze, but the initial results raised more questions than they answered, and the scientific community found itself walking the razor's edge between discovery and delusion. Extraordinary claims require extraordinary evidence, a principle that had guided SETI research for decades. But how do you define extraordinary when you're dealing with phenomena that have never been observed before? The challenge wasn't just analyzing the data from 3 Atlas, it was developing entirely new frameworks for evaluating claims about non-human intelligence. The scientific method had evolved sophisticated tools for avoiding false positives. Pre-registered analyses forced researchers to commit to specific hypotheses before examining data, preventing the unconscious cherry-picking that could turn noise into signals, blind injections, fake signals inserted into data sets without researchers. Knowledge tested whether detection algorithms could distinguish real phenomena from artifacts. Independent analysis pipelines developed by different teams using different software provided cross-validation for critical results. If 5 different groups working with the same data but independent methodologies reached the same conclusions, the findings gained credibility. If they disagreed, more work was needed. The competing models for 3 Atlas fell into 3 broad categories, each with its own predictive framework and observational tests. The engineered light sail hypothesis proposed that 3I Atlas was an artificial construct, possibly automated, designed for interstellar communication or exploration. This model explained the object's extreme geometry, controlled rotation, thermal management, and radio emissions. It predicted that detailed analysis would reveal materials or structures inconsistent with natural formation processes. The exotic natural fragment hypothesis suggested that 3I Atlas represented a previously unknown category of interstellar object, perhaps debris from a stellar collision or the disruption of a comet containing unusual materials. This model could potentially explain the object's anomalous properties without invoking artificial origins. It predicted that spectroscopic analysis would eventually reveal natural, if rare, formation mechanisms. The normal comet hypothesis maintained that 3E Atlas was fundamentally similar to 2E Boris, with apparent anomalies resulting from observational artifacts, selection biases, or misunderstood natural processes. This model predicted that more detailed analysis would reveal conventional cometry behavior masked by the object's unusual orientation and composition. Each model scored differently against the accumulating evidence. The radio emissions strongly favored artificial origins. Natural processes rarely produced narrowband signals with mathematical modulation patterns. The controlled rotation and thermal management also seemed more consistent with engineered systems than natural objects. But the spectroscopic data remained ambiguous. While 3I Atlas showed unusual surface chemistry, determining whether these materials were natural or artificial required understanding formation processes that might not exist anywhere else in the galaxy. Exotic didn't necessarily mean artificial. The Encounter mission had provided crucial new data. Close approach. Imaging revealed surface structures that appeared organized rather than random patterns that suggested design rather than natural weathering or collision damage. But pareidolia, the tendency to see patterns where none exist, had fooled humans throughout history. The canals of Mars had seemed obviously artificial to 19th century astronomers. Laser communication experiments during the encounter provided the most tantalizing results. When the spacecraft transmitted structured light pulses toward 3I Atlas, the object's surface reflectivity changed in patterns that appeared to correspond to the transmission sequence. But optical effects in space environments could be complex, and confirming that the changes were responses rather than coincidences required statistical analysis that was still ongoing. The historical context of Oumuamua provided both guidance and caution. That first interstellar visitor had shown non-gravitational accelerations that initially seemed inexplicable. Scientists proposed exotic explanations, fragments of alien technology, hydrogenisbergs, even suggestions that Oumuamua might be a light sail from another civilization. But careful analysis by Dr. Marco Michichelli and his colleagues published in Nature in 2018 demonstrated that the accelerations could be explained by conventional outgassing from a comet nucleus. The unusual geometry and lack of visible coma had initially disguised Oumuamua's cometary nature, but detailed modeling showed that natural processes could account for all observed properties. The lesson was sobering. Extraordinary hypotheses should be the last resort, not the first. Natural explanations, even unlikely ones, deserved serious consideration before invoking extraterrestrial intelligence. 2I Boris had provided a useful contrast, a clearly normal interstellar comet that behaved exactly as theory predicted. Its composition matched solar system comets, its outgassing followed standard models, and its trajectory showed no anomalies. Borisov demonstrated that most interstellar visitors would probably be unremarkable, making the apparent anomalies of 3 Atlas even more intriguing. The ongoing controversy over interstellar meteors added another layer of complexity to the analysis. The 2014 fireball designated IM-1 had been classified as potentially interstellar based on its high velocity and unusual trajectory. Dr. R.V. Lobb's expedition to recover material from the impact site had produced spherical fragments with compositions that some researchers claimed were artificial in origin. But the IM-1 spherals remained controversial. Other scientists argued that the unusual compositions could result from terrestrial contamination or normal meteoritic processes under extreme conditions. The need for larger samples and independent laboratory analysis had slowed progress toward definitive conclusions. These experiences informed the analysis of 3I Atlas data. Every anomaly required multiple independent confirmations. Every unusual measurement needed to be reproduced by different instruments and analysis techniques. the scientific community was determined to avoid both false positives and false negatives, claims of alien contact that later proved wrong or dismissal of genuine phenomena due to excessive skepticism. Bias audits became routine parts of the analysis process. Teams of researchers would exchange datasets and analysis responsibilities, searching for systematic errors or unconscious assumptions that might skew results. Adversarial collaborations brought together scientists with fundamentally different interpretations of the data, forcing them to identify the observations that might distinguish between competing hypotheses. The process was slow and sometimes frustrating, but it was working. 6 months after the encounter, a preliminary consensus was emerging from the scientific community. The evidence for artificial origins was suggestive, but not conclusive. Several key observations remained unexplained by natural processes, but the possibility of exotic natural phenomena couldn't be ruled out. The interim language for public communication was carefully calibrated. 3 atlas exhibits properties that are difficult to explain through currently understood natural processes. While the possibility of artificial origins cannot be dismissed, more observations and analysis are needed to reach definitive conclusions. But even this cautious phrasing carried profound implications. For the first time in human history, the scientific community was seriously considering the possibility that we had encountered technology from another civilization. The burden of proof was enormous, but the potential discovery was worth the most rigorous investigation humanity could mount. The knife edge between proof and pareidolia remained sharp, but with each new analysis, each independent confirmation, each failed attempt to debunk the anomalies, the balance was slowly shifting toward a conclusion that would change everything we thought we knew about our place in the universe. Part 10. The message unfolds content, form, and meaning. What 3 Atlas was trying to tell us became clear only through months of painstaking analysis, and the message was both more complex and more practical than anyone had expected. The communication wasn't a greeting or a philosophical statement. It was an instruction manual. Dr. Yuki Tanaka at the Tokyo Institute of Technology led the international decryption team. Her background in information theory and signal processing made her uniquely qualified to tackle the layered structure of the visitor's transmissions. What initially appeared to be simple prime number sequences revealed themselves as headers for more complex data packets, each one building upon the mathematical concepts established in earlier transmissions. The first layer was mathematical foundation, establishing shared concepts that would allow more sophisticated communication. Prime numbers gave way to algebraic relationships, then to geometric principles. The visitor was teaching us its mathematical language before attempting to convey more complex ideas. The second layer introduced physical constants, the fine structure constant, Planck's constant, the speed of light. But these weren't just confirmations of universal knowledge. They were presented with precision that exceeded humanity's current measurements, suggesting our visitors possessed more accurate understanding of fundamental physics. The third layer was where the message became interesting. The visitor began transmitting what could only be described as technical specifications, detailed instructions for constructing a radio beacon with capabilities far beyond current human technology. The specifications were elegant in their consideration for human limitations. Rather than assuming unlimited resources or advanced materials, the design used technologies that 21st century Earth could reasonably develop. The beacon would require a large array of precisely coordinated transmitters, but the individual components were within reach of human engineering. More remarkably, the design included optimization for Earth's specific rotation period and magnetic field characteristics. This wasn't a generic template. It was customized for our world, suggesting the visitors had been studying Earth's properties in detail before making contact. The The fourth layer contained what Dr. Sarah Kim at MIT called the network map, a description of how the proposed beacon would interface with what appeared to be a galaxy-wide communication system. The map showed relay nodes positioned at strategic locations throughout local space, each home described by precise astronomical coordinates. Some of these coordinates corresponded to known stars. Others pointed to empty regions of space where gravitational lensing effects might focus and amplify signals across interstellar distances. The visitor was describing a communication network that used the galaxy's own structure as infrastructure. The ethical payload embedded throughout the technical specifications revealed sophisticated understanding of biological worlds. Their message included symbols and concepts that clearly referred to living systems, planetary environments, and what could only be interpreted as conservation principles. There were implicit warnings about maintaining electromagnetic quiet near biological surfaces, suggestions that powerful transmitters should be positioned away from inhabited worlds. The encoding itself was a masterpiece of information theory. Every data packet included multiple layers of error correction, ensuring that the message could be recovered even if large portions were corrupted or lost. Temporal scaffolding allowed the transmission to be assembled correctly despite interruptions, Doppler shifts, and the intermittent visibility of the moving transmitter. Explicit markers identified byte order, dimensional units, and coordinate systems, preventing the ambiguities that could arise when species with different mathematical traditions attempted to communicate. The message was designed to be decoded by any intelligence capable of detecting it, regardless of their specific technological development path. But the most intriguing aspect was what the message didn't contain. There were no personal communications, no cultural artifacts, no attempts at small talk or philosophical exchange. The visitor's message was purely functional, a technical manual for joining what appeared to be an established interstellar communication network. The implications were staggering. Humanity wasn't just receiving its first message from another civilization. We were being invited to join a community of intelligences that had been operating across the galaxy for an unknown period of time. Public participation in the decryption effort had proved invaluable. Citizen science platforms allowed thousands of volunteers to contribute to different aspects of the analysis. Pattern recognition tasks were distributed to classroom students worldwide. The collaborative effort represented the largest coordinated intellectual challenge in human history. Convergent translations emerged as different teams, working independently, reached similar interpretations of key portions of the message. This redundancy provided confidence that the decryption was proceeding correctly despite the unprecedented nature of the communication. The Deep Space Optical Communications demonstration aboard the Psyche mission had provided crucial experience with high-bandwidth optical communication across interplanetary distances. Those lessons informed speculation about how the visitor might extend the conversation beyond simple radio signals to more sophisticated data exchange. But perhaps the most significant aspect of the message was its implicit deadline. The technical specifications for the beacon included temporal coordinates, precise timing requirements for initialization and synchronization with the broader network. If humanity wanted to join the galactic community, we had a limited window in which to build and activate our node. The decision point was approaching rapidly. The visitor had provided us with detailed instructions for constructing our own interstellar communication system. The technology was challenging but achievable. The question was whether humanity was ready to announce its presence to whatever civilizations might be listening across the galaxy. Building the beacon would be irreversible. Once activated, Earth's participation in the galactic network would be permanent and visible to any intelligence monitoring the communication channels. We would no longer be an isolated world shouting into the darkness. We would become part of something vast and ancient and utterly beyond our current understanding. The choice, ultimately, was simple. remain alone or join the conversation that had been taking place among the stars since before human civilization began. Part 11, Second-Order Effects, Technology Law and Power. The moment humanity seriously considered building an interstellar beacon, everything changed. Not just our technology, but our politics, our economics, and our understanding of what it means to be human. Engineering teams worldwide began rapid prototyping of the technologies described in 3 Atlas's message. The beacon specifications pushed the boundaries of human manufacturing, but not beyond them. Ultra-thin metamaterials precisely engineered at the nanoscale would form the primary transmission elements. Low-noise oscillators locked to atomic frequency standards would provide the stable references needed for galaxy-wide communication. The most challenging requirement was coordination. The beacon would consist of thousands of individual transmitters, distributed across hundreds of kilometers, all operating in perfect synchronization. The timing precision required nancond accuracy maintained over interplanetary distances demanded advances in both quantum timekeeping and distributed control systems. Cooperative radar-laser hybrid systems emerged as a crucial technology. By combining radio transmissions with precisely timed optical pulses, the beacon could achieve the bandwidth and power requirements specified in the visitor's instructions. The dual-mode approach also provided redundancy. If one system failed, the other could maintain communication. But every breakthrough in beacon technology carried dual-use implications. The same precise timing systems needed for interstellar communication could guide intercontinental ballistic missiles with unprecedented accuracy. The high-power transmitter arrays could potentially interfere with satellites or even serve as directed energy weapons. Planetary defense advocates argued for transparency protocols that would allow international monitoring of beacon construction and operation. The technology was simply too powerful to develop in secret. Any nation or organization building interstellar communication systems would need to submit to inspections and verification procedures. Legal frameworks struggled to catch up with technological reality. The Outer Space Treaty of 1967 governed activities in space, but said nothing about communicating with alien civilizations. The Liability Convention of 1972 addressed damage from space objects, but couldn't anticipate disputes over interstellar messaging rights. Model legislation began emerging from legal scholars worldwide. Contact governance treaties proposed for adoption through the United Nations would establish international protocols for extraterrestrial communication. The frameworks borrowed heavily from existing arms control and environmental protection agreements, but adapted for the unique challenges of interstellar diplomacy. The question of who speaks for Earth became more than philosophical. With the visitor's beacon specifications in hand, multiple nations and organizations began claiming authority to build and operate humanity's node in the galactic network. NASA proposed an international consortium similar to the International Space Station Partnership. China announced plans for an independent beacon system. Private companies submitted their own proposals, arguing that commercial competition would accelerate development. Data rights emerged as a critical issue. Would the beacon's transmissions be public information available to all humanity, or would the nations and organizations that built the system control access to interstellar communication? The precedent established with Earth's first beacon would likely determine communication, governance for generations. Economic implications rippled through every sector. The rare Earth elements required for beacon construction triggered commodity price spikes that persisted for months. Lithium, already essential for battery technology, became even more strategic as engineers realized its importance for quantum frequency standards. But the greatest economic shift was psychological. Investment horizons extended from quarters and years to decades and centuries. Companies began planning for market opportunities that might not emerge until their great-grandchildren were making business decisions. The cosmic perspective fundamentally altered how humans thought about time and value. Cryptocurrency markets spawned hundreds of galactic coins designed for interstellar commerce. Most of them obvious scams, but some representing serious attempts to create communication protocols that could function across species barriers. The mathematical requirements for galaxy-wide consensus mechanisms pushed blockchain technology to unprecedented directions. Religious and philosophical institutions grappled with humanity's changing status. Were we still made in God's image if we shared the galaxy with other intelligent beings? Did moral obligations extend to civilizations we had never met but might soon join? Theological seminaries found themselves offering courses in astroethics and interspecies communication. Educational systems experienced unprecedented demand for physics, mathematics, and engineering programs. Students who had never shown interest in technical subjects suddenly wanted to understand the science behind interstellar communication. Community colleges began offering beacon literacy courses, teaching the basic concepts needed to participate in humanity's cosmic conversation. Environmental considerations complicated beacon planning. The transmission arrays would require enormous amounts of electrical power, potentially gigawatt during peak operation. Carbon-aware power sourcing became essential to avoid worsening Earth's climate problems while reaching for the stars. Solar farms and fusion reactors received new investment as the environmental movement allied with space communication advocates. Ground-based transmission systems raised concerns about electromagnetic effects on wildlife. Birds, whales, and other animals that navigated using Earth's magnetic field might be disrupted by powerful radio emissions. Careful site selection and transmission protocols would be needed to minimize ecological impact. The cislunar region became humanity's newest frontier for beacon development. The far side of the Moon offered natural radio shielding from Earth's interference, making it an ideal location for sensitive receiving equipment. Near Earth, asteroids could provide raw materials for construction without the environmental costs of Earth-based mining. Space traffic management systems, already strained by expanding commercial activity, faced new challenges from beacon-related infrastructure. Orbital debris from construction activities could threaten existing satellites. Communication interference between beacon systems and conventional spacecraft required careful frequency coordination. International cooperation emerged as both necessity and opportunity. No single nation possessed all the resources needed for rapid beacon construction. Successful projects required sharing of technology, funding, and expertise across traditional political boundaries. The beacon became a catalyst for the kind of global collaboration that had been elusive for purely terrestrial challenges. But cooperation carried risks. Shared beacon systems would need governance structures that could survive political changes and international conflicts. What would happen if participating nations disagreed about message content or transmission priorities? How would humanity resolve disputes when the consequences might affect our standing in a galactic community? The institutional frameworks developed for beacon governance would likely shape humanity's approach to space development for centuries. The precedents established, openness versus secrecy, competition versus cooperation, national interests versus species interests, would influence everything from asteroid mining to interstellar exploration. As construction timelines compressed and launch dates approached, humanity found itself transforming not just its technology but its identity. We were no longer an isolated species shouting into the void. We were preparing to become citizens of a galaxy-spanning civilization whose true scope we were only beginning to understand. The implications extended far beyond the beacon itself. Every aspect of human society, from education and economics to governance and philosophy, was adapting to the reality that we shared the universe with intelligences whose capabilities might dwarf our own. the second-order effects of contact were reshaping civilization itself. Part 12. After the Echo, Who We Choose to Be. 2 years after the first radio exchange with 3 Atlas, humanity stood at a crossroads that would define our species. For millennia to come, the visitor had departed our solar system in early 2027, accelerating along its hyperbolic trajectory toward destinations unknown. But its message remained, encoded in our databases and our collective memory, a blueprint for joining a galactic community we had never imagined existed. The decision before us was deceptively simple: build the beacon or remain silent. But the implications of each choice reached into every aspect of human civilization. 3 scenarios dominated policy discussions across the world's capitals and academic institutions. The conservative path advocated maintaining listening posts and expanding our passive SETI capabilities, but avoiding any active transmission that might attract unwanted attention. Proponents argued that we needed decades or centuries to better understand the galactic community before announcing our presence. Better to observe quietly, learning about our potential neighbors before revealing our location and capabilities. This approach carried obvious appeal. It was safe, reversible, and allowed humanity to develop on our own timeline. We could continue advancing our technology, expanding through the solar system, and building the economic and social foundations needed to engage with more advanced civilizations as equals rather than supplicants. But critics pointed out the costs of isolation. The beacon specifications provided by 3 Atlas represented technology centuries ahead of human development. Refusing to engage might delay our advancement indefinitely, leaving us permanently behind civilizations that had already been communicating for millennia. The participatory path proposed building a modest, carefully controlled beacon system that could be activated or deactivated based on humanity's collective decision-making. This middle course would establish our capability to join the galactic network without immediately committing to active participation. The technical requirements were significant but achievable. A distributed array of transmitters coordinated by quantum timing systems positioned in space to avoid interference with Earth's biosphere. The beacon would operate at minimum power levels initially, announcing our presence but not overwhelming nearby communication nodes with inexperienced. Transmissions governance structures would ensure that no single nation or organization controlled humanity's voice in galactic affairs. Message content would require international approval through expanded UN frameworks. Transmission schedules would balance scientific exploration with diplomatic caution. The ambitious path called for full commitment to interstellar communication. Within a decade, proponents argued that the visitor's beacon specifications included time-sensitive coordination requirements. If humanity wanted to join the galactic network effectively, we needed to move quickly while the visitor's message remained current and relevant. This approach promised rapid technological advancement and immediate access to whatever knowledge the galactic community was willing to share. Early participation in interstellar communication might provide humanity with scientific and technological advantages that could solve our most pressing problems: climate change, resource depletion, the challenges of expanding beyond Earth. But the risks were enormous. Full participation in galactic communication would make Earth permanently visible to any intelligence monitoring the network. We would be committed to relationships and obligations we couldn't fully understand. Withdrawal from the network once we had joined might prove impossible or carry severe consequences. The debate transcended traditional political boundaries. Progressive environmentalists found themselves aligned with conservative military strategists in favoring the cautious approach. Libertarian technologists allied with international diplomats in supporting measured engagement. The cosmic perspective had scrambled conventional political categories. Public opinion remained divided but engaged. Polling consistently showed majority support for some form of beacon construction, but with significant variations based on specific proposals and implementation timelines. The most popular approach combined elements of all three scenarios, building beacon capability quickly, but activating it gradually with extensive safeguards and international oversight. The Galileo project, originally conceived to search for signs of extraterrestrial technology, evolved into a standing program for TECHNO, signature detection and analysis. Its expanded mission included monitoring for additional interstellar visitors, analyzing the beacon specifications provided by 3i Atlas, and developing the scientific foundation for future contact scenarios. Funding mechanisms emerged from unexpected sources. Tech billionaires who had previously focused on Earth orbit ventures redirected investment toward interstellar communication. Nations that had never participated in space programs began contributing to beacon development consortiums. The distributed nature of the required technology allowed smaller countries to make meaningful contributions through specialized manufacturing or research. Legal frameworks continued evolving through international negotiations. The outer space, treaties' restrictions on national appropriation of celestial bodies were extended to cover interstellar communication nodes. New protocols governed the sharing of alien technology and the distribution of any benefits from galactic participation. The question of institutional stewardship became critical. Beacon systems designed to operate for centuries required governance, structures that could survive political changes, economic upheavals, and social transformations. The precedent of maintaining continuity across generations would determine whether humanity could be a reliable member of any galactic community. Scientific preparations accelerated regardless of policy decisions. Radio telescopes continued monitoring for additional visitors and attempting to detect the broader galactic communication network described in 3 Atlas's message. Gravitational lensing experiments tested whether stellar focal lines could indeed amplify signals across interstellar distances as the visitor's specifications suggested. Prototype beacon components underwent testing in Earth orbit and at the lunar Lagrange points. The technical challenges were yielding to human ingenuity, but the engineering timeline remained formidable. Full beacon capability would require at least a decade of focused development, probably longer. Psychological support systems emerged to help individuals and communities adapt to the cosmic perspective. Contact counseling became a recognized specialty, helping people integrate the knowledge that humanity was part of a larger galactic civilization. Support groups formed organically, bringing together people who were struggling to find meaning and purpose in a suddenly vast universe. Educational curricula evolved to prepare students for a future that might include routine interstellar communication. Children who would come of age in the 2032nd and 2042nd began learning mathematics and physics with the explicit understanding that they might use these tools to communicate with alien intelligences. The generational divide was striking. Older adults often struggled with the implications of contact, while younger people adapted quickly to the idea of galactic citizenship. Children seemed almost unsurprised by the revelation that other intelligences existed, as if they had always known and were merely waiting for adults to catch up. As the decade progressed, humanity's choice crystallized around a fundamental question of identity. Were we explorers or preservers? Did we define ourselves by our willingness to reach into the unknown, or by our commitment to protecting what we had already achieved? The answer, when it came, reflected both impulses. Humanity would build the beacon, but carefully. We would join the galactic community, but on terms that preserved our autonomy and protected our homeworld. The compromise satisfied neither the most ambitious nor the most cautious, but it reflected a species-wide consensus about who we wanted to become. The night sky looked different now. The points of light that had once seemed distant and lifeless were revealed as potential homes to intelligences whose messages might already be traveling toward Earth at the speed of light. The cosmos had become a neighborhood vast beyond comprehension, but no longer empty. In the end, perhaps that was 3 Atlas's greatest gift. Not the technology to join a galactic civilization, but the knowledge that we had never been alone. Somewhere among the stars, other minds were asking the same questions, facing the same challenges, reaching toward the same distant lights that had inspired human dreams since we first looked up in wonder. The conversation that began with humanity's accidental radio leakage and continued with 3 atlas's carefully crafted response was far from over. It was, in fact, just beginning. The real question wasn't whether we would join the galactic community, but what kind of neighbors we would choose to be. As Earth's first interstellar beacon powered up for its initial test transmission, a quiet carrier tone stepped upward through prime number frequencies. Our species' first intentional words in a conversation that had been waiting for us since. Long before we learned to speak. The signal pulsed steadily into the void, a small but deliberate announcement that humanity was awake and listening. For the first time, the vast silence of space seemed less intimidating, replaced by a sense of possibility. Every scientist, engineer, and dreamer who had contributed to the beacon's creation felt a quiet pride, knowing their work had become part of something far larger than any nation, any ideology, or any single lifetime. Yet even as the transmission spread across interstellar distances, questions lingered. Would anyone hear us? Would we recognize the replies if they came? And more profoundly, what stories would those replies tell about other civilizations, about the paths they had chosen, the mistakes they had survived, and the wisdom they had gained? Humanity's role in the galaxy remained undefined, but that uncertainty was no longer paralyzing. Instead, it was a space for curiosity, for learning, for careful but bold engagement. We had taken the first step, not as conquerors, not as supplicants, but as neighbors extending a hand across the cosmic expanse. As the beacon continued its rhythmic pulse, Earth itself seemed to hum with anticipation. Children read textbooks that hinted at the knowledge of distant worlds. Families gazed at the stars with a new sense of kinship. Even the night air seemed charged with a subtle expectancy, as if the universe had shifted slightly, leaning closer to listen. Perhaps in the end, 3 Atlas had offered more than a blueprint for interstellar technology. They had given humanity a mirror, reflecting not just what we could achieve, but who we might become. And in that reflection, for the first time, we understood that the journey into the cosmos was not about reaching other worlds, but about discovering the full measure of ourselves. The conversation that had begun with an accidental whisper of radio waves and was now amplified through centuries of ingenuity was only beginning. Somewhere out there, other minds were waiting, and somewhere on Earth, humanity was ready to meet them, not with fear, but with wonder. The beacon's tone shifted subtly, a harmonic signature designed to endure light years of travel. And as it vanished into the black, the stars above no longer seemed distant. They seemed familiar, almost like neighbors waving back.